Hello, everyone. Today we will be discussing Chapter 1, Digital Systems and Information. We will be talking about the general computer. So when you come in to these slides, we have an index slide here, and you can click on whatever topic we're going to be talking about. So today we're going to talk about the general computer, and that will take us right to our topic. Okay, digital systems are everywhere. We are all very familiar with digital systems. They store, move, and process information, such as weight, temperature, pressure, velocity, flow, sound intensity, frequency. The list goes on and on and on. A digital system is defined as any system which can serve a particular function using digital logic elements. Digital systems, as I mentioned, are everywhere: communications, multimedia, consumer electronics, healthcare, defense, software, security, education, churches, and our homes. Our light bulbs have digital systems. Our refrigerators, microwaves, ovens, everything has a digital system. Our cars. Information is represented as either digitally or as analog. An analog representation is a waveform. It's continuous, capable of taking on possible values over a defined range, whereas digital is discrete. It's values that occupy a finite number of values over a range. And while digital is still analog in terms of the actual waveform, it is interpreted as binary. So what does this mean, being interpreted as binary? Binary means there are two values. So a waveform is interpreted as a high or a low, or logic 1 or logic 0, or true and false, or 5 volts or 0 volts, 3.3 volts, 0 volts. The list only includes two values, so it's a binary representation of the analog voltage. Digital signals, as I said before, are analog in terms of the actual waveform. However, the way digital signals are represented and interpreted are binary. As we know, analog waveforms are never absolutely perfect. So we have to set boundaries on the waveforms. For instance, we could have a waveform which is 0 volts to 1 volts, 0 volts minimum, 1 volt maximum. And a digital one, we could say, is any signal that is greater than or equal to 0.9 volts. We'll call it a digital one. Any signal that is less than or equal to 0.1 volts, we would call a digital 0. Anything in between is undefined. So if a signal comes in between those two values, we would not have a definition for it. Faster signals give sharper digital signals. Let's take a look at this example here. Which is examples of voltage ranges and waveforms for binary signals. We have an analog signal that looks something like this. And this is an extremely fast signal. So how do we know it's extremely fast? Look at the slope. It is very easy to distinguish the high value and the low value, and it looks very much like a digital signal. Here we have an example of an analog signal, which ranges from minus 0.1 to plus 1.1. And in this example, any signal above 0.9 would be considered a high. Any signal below 0.1 would be considered a low. In the second example here, any signal above 0.6 would be considered high. Any signal below 0.4 would be considered low. If we had a slow signal, it would have a slope that looks something like this, where it would even out or level our waveform. That's harder to distinguish between a high and a low, especially this one, which has very strict limits or boundaries. What are some benefits of binary? Correct circuit operations can be achieved with significant variations in values of the output voltages and input ranges. The resulting transistor circuits are simple. They're easy to design. They're extremely reliable. Why are they extremely reliable? Because we can have repeatable results. The same set of input values always gives the exact same set of outputs. And what are the input values and output values? 0, 1. Noise and small variations do not affect the results. This is not the case for multi-valued or analog circuits, which can have noise, and as they age, there would be more noise. The block diagram represents the general computer. The three main blocks included in a digital computer are the CPU, which consists of the control unit and the data path. The data path is typically called an arithmetic logic unit, and these two units are the CU and the data path are on a CPU, and FPU, MMU. These are all things that we will be discussing. Memory is typically a term used for RAM, but in this case, we are also using it for registers, cache, and RAM. And input-output, while we know this as keyboards, etc., in this particular block diagram, it would be something like a hard drive, which is offering input to a CPU and output from a CPU. Memory stores programs as well as input, output, and intermediate data. The data path performs arithmetic and other data processing operations as specified by the program, also known as an arithmetic logic unit, or ALU. The control unit supervises the flow of information between the various units. And as I said before, the data path and the CU comprise the CPU, which is the central processing unit. And this is a component that most of us are familiar with. But as I mentioned, there is an MMU and FPU, floating point unit, and memory management unit. Input-output is the transfer of programs and data performed by devices which may be digital or analog, such as keyboard, LCD screens, DVD drives, USB, flash drives, scanners, printers, optical sensors, and actuators. So the last two here mentioned are analog, the others here are digital, and this is not a complete list of input-output devices, and I'm realizing here there's not even hard drive listed. The block diagram of an embedded system. Embedded systems are smaller digital systems within a computer, within what we typically know as digital systems. So a digital system is rarely just one system. We have several. And at the center of the embedded system is the microcomputer, microcontroller, or digital signal processor, whatever term. All three terms are acceptable. And an embedded system has input, which could be analog or digital. However, the microprocessor or microcontroller can only receive digital. So if there is analog input, it would have to go through an analog to digital converter. And part of the embedded system would be some external memory from the microcontroller, which could be cache or registers. If the final output is analog, then there would be a digital to analog converter. If the final output is digital, then there's no converter needed. Embedded systems are integral parts of other products. You could have multiple embedded systems within a computer system. Human interface is non-existent or very limited. The microcomputer is central to the embedded system with permanently stored software and provide only the functions required for the product. Input devices transform inputs, which are analog or digital from the product or outside world into digital or analog signals. And we use A to D and D to A converters to do this. And as an example, all right, this text, the copyright value here, date is 2016. The text is 2014, so it's a little older. And a late model automobile contains more than 50 microcontrollers, each controlling a distinct embedded system. So that's an example. Refrigerators have embedded systems these days. Let's look at some examples. Copiers, fax machines, UPC scanners, vending machines, teller machines, communications, networking would be wireless access points, network routers, satellites. I think of communications as telephone systems. Your smartphone is listed as personal, but there are base station towers that phone wires for communications for your cell phone. Games and toys, video games, home appliances, dishwashers, microwave, your alarm. Does anybody have an alarm anymore? Oven, refrigerator, media. Okay, I don't think anyone uses a CD player anymore or DVD players, but they have embedded systems. Or TVs, if anyone uses a TV. Digital cameras, digital video cameras, no one uses those anymore, but we do have them in our phones. Medical equipment, transportation and navigation, our automobiles, our airplanes, planes, trains, and automobiles. Our stoplights, there are cameras everywhere, and they are collecting data. We have layers of abstraction. Digital systems are very complex. Leading edge integrated circuits have billions of transistors. Designing an integrated circuit one transistor at a time is impractical. How do we design complex systems? We make abstractions. Computer systems such as the generic computer can be viewed as several layers of abstraction from circuits to algorithms. Each layer of abstraction hides the details and complexity of the layer below. This removes unnecessary implementation details about a component in the system. That way, the designer can focus on the aspects of the component that matter. Lower layers can be modified without worrying about changing the layers above them. Typical layers of abstraction in computer systems at the lowest level would be transistor circuits, logic gates, register transfers, microarchitecture, instruction set architecture, operating systems, programming languages, and algorithms. This textbook deals with the layers from logic gates up through operating systems. And this course, we will deal with logic gates, register transfers, and microarchitecture. Transistors. The computer is made up of integrated circuits such as the processor. I had mentioned that before, and there can be billions of transistors in a processor. Integrated circuits are comprised of logic gates, and the next level logic gates are made of transistors. The transistor is an electronic solid-state device that can amplify an electric signal. It can be thought of as a switch with an on or off mode. Very small nanoscale dimensions. So in order to get billions in an integrated circuit, we use robots. You will learn more about transistors in your future electronics classes. And what you will work with are not nanoscale, but they look something like this. This is an example of a BJE transistor, but there are several types of transistors, and you will learn, know, and love them. Logic gates are basic building blocks in a digital system. We have three fundamental gates: and, or, and not. These three fundamental gates then allow us to develop more gates, which we will be discussing in, I think, chapter 2. Logic blocks can be thought of two types as combinational and sequential. And again, we will discuss this in chapter 2, but combinational is input, output. Sequential requires some memory. And we will use flip-flops and latches when we get to that. Logic blocks have one or more inputs and one or more outputs. So for instance, the AND gate has 2 inputs and 1 output, and the OR gate has 2 inputs and 1 output. The NOT gate is also known as an inverter gate, and it has 1 input and 1 output. Our integrated circuits have a number of inputs here, but the values of the inputs will be either 0 or 1. And an integrated circuit can have multiple outputs, and the values for those outputs would be 0 and 1. This is meant to be an introduction to the general computer and what we will be discussing this semester. And our next topic will be number systems. And we will start with the binary number system. But this concludes the introduction for the general computer.